So hi guys, today we will be trying to solve this. Yeah, so this is, I think, this is a question NBHM, I think 2023, and it's question number 37. Right, as you can see from the question. Now, it says basically like, oh, this is a true and false type. So it says that let fz be an arbitrary non-constant entire function on the complex plane. So, so it's actually mentioned non-constant, arbitrary non-constant and non-constant entire. Uh, it is possible for fz. Uh, so the first option says that it is possible for fz not to take any real value. So, so basically it says that like right. So basically f of c uh, is contained in so So if he f is non-constant entire, like it says that it is possible for the image of f to be contained in C, to be contained in C minus R. Like this is clearly not possible because right. So let me just draw this. This is pretty simple because right. So only thing this part. So image is actually missing all this part. Now we know that image of a non-constant image of a non-constant entire function is dense. So but this is dense, right? Because you can take any point here and draw a ball. So yeah, it will actually intersect. It dense in C, right? But it misses uncountable number of points. So yes, image is dense, but like a non-constant entire function misses. So let me just write this. Uh, uh, Non-constant entire function f, right, misses at most 1 point, right? So, but it is missing such I mean, a bunch of points, like the whole real life. So this is not possible. So not possible. So this is false. Right, like we can actually see that e to the power z is entire, right? E to the power z is entire because we have this z square by 2 factorial, 1 factorial, z cube by, and so on. But it never, it misses zero. So it can miss at most 1 point. This is Picard's theorem. So yeah. On the other hand, it might not miss any point as well. For instance, like we can just take sin z and cos z, they are completely onto functions. So yeah, so option A is false. Now, like okay, option 2 is given, like number B is given as, like option B, a complex number z naught is called a local minimum of fz. So basically, if fz naught, a mod of fz naught less than equals to f mod of fz for all z in some set u around z naught, right? So it's a local minimum. Okay. So basically, let's say we have this. So z naught is called a local minimum. So suppose we have something of neighborhood like this. So f of z naught here, so it will satisfy this, right? Yeah, because for any like uh, let's say z here. So let's say z, and this is, yeah, and let's say this is u. So so basically, what will happen if z naught is a local minimum? Mod of f z naught is less than equals to mod of f z, right? So it is given. Okay, we will get a basically neighborhood in some open set. So now the question is, if z naught, sorry, if z naught is a local minimum of fz, then f z naught is zero. And remember, the function is given non-constant entire. So how can we show this? Okay, so right. So let us suppose. So uh, let us suppose that. So we will try to use contradiction, right? We will try to use contradiction, right? Uh, Let us suppose that f of z naught unequals 0, right? Then basically f of z naught mod is actually greater than 0, right? It will be positive, and since it's non-zero, f of z naught is non-zero, f of z naught is greater than 0. Now, okay, let me just draw this first. So let's say this is u, and this is z naught, okay? and let's say this is some point is an arbitrary z, okay, which actually belongs to this. So uh, so if z not unequals 0, then this will be greater than 0. Now in our question is given, now since it's since z naught is local minimum by definition, local minimum by definition, we have f of z like mod greater than equals to f of z naught, right? Mod of f of z naught which is greater than 0, right? So this is true for all z belongs to u. Okay, so basically, mm, if f of z has no zeros inside u, right? So since f of z has no zeros inside u, right, basically, which means that f of z unequals 0 for all z belongs to u, it essentially means that we can apply minimum modulus principle, right? We can apply minimum modulus principle. So, and we know applying applying minimum modulus principle, okay, let me write it properly. Since fz is non-zero, right, and if and also given since f is entire, f is analytic on u, right, and it does not vanish inside u. So now, so we can apply minimum modulus principle. So applying minimum modulus principle gives us that if z equals to if z naught for all z belongs to u, right? That is if z is constant. And this is true because, right, because like, since the function is entire, so it's analytic on u, and since analytic on u and continuous, and it is also continuous at the boundary. So if z is continuous at, so del u, right, at the boundary of this, as it is continuous at del u, so minimum will be attained at del u, but we already know, but we know that since z naught is a local minimum, right? So given since z naught is a local minimum, that is not possible, right? So everything had to be constant, but it has to be constant, right? And what will be the value? Like, that is clearly fz naught, right? So yeah, since Z naught is a local minimum and using minimum modulus principle, like the like the minimum value will be attained at boundary, but that is not the case here. The only possible thing we can do is the only possible way the function such function exists is that if z has to be constant, and it has to be equal to this f of z naught, right? Okay, so now, so basically, okay, so in this whole u region, right? Fz is constant in this region. Basically, Fz is constant. So, I mean, in this open set, Fz is constant. So we can just apply, yeah, identity theorem. Applying, okay, applying identity theorem, we can extend this. We can extend this to the whole complex plane, which will imply Fz is constant. But in the question, it's already given that Fz is non-constant, entire function. So our assumption is false. Okay, so our assumption is false, and Fz naught will be equals to 0. So this is true. Now we can, okay, so this is the proof. So we can also, instead of using minimum modulus, we can also use maximum modulus as well. So this is the statement. I've written it down, like non-constant function, analytic in a bounded region, and continuous. The max is attained at the boundary, right? So since if z unequals 0 in u, so we can just define gz to be 1 by fz, right? So, and we can just yeah, and also, right, also, uh, if z mod greater than equals to fz naught, right? Mod for all z belongs to u. So which will imply uh, gz naught, which is nothing but 1 by fz naught, right? To be greater than equals to uh, gz, which is nothing but 1 by fz, sorry, mod of gz naught. Okay, so right. So basically, gz naught is greater than equals to gz for mod of gz for all z belongs to you. So yeah, so now we can just apply maximum modulus principle. So maximum modulus principle says that if f is a non-constant analytic function in region D, then fz has no maximum in D. Okay, so and this part, right? So if it's continuous at the boundary, then the maximum value of mod f will be attained on the boundary of that region or the open set D. So yeah, so 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 this actually contradicts maximum modulus principle. So which will imply that gz is constant. Gz is constant, which will imply fz is constant on A, and then we can again use the identity theorem. So we can use both, like uh, yeah, like we can use both maximum modulus principle or minimum modulus principle. It doesn't matter. So first option will be false and second option will be true. Yes, so I think this is a solution.